Right, our next stop in our tour of light is to talk about color. So in previous videos, I've talked about how color can be formed by light reflecting off of objects. So we're going to talk about how colors are formed, how we see them, and how we can create color. So first thing is that color is a white light, for example, the white screen that you see right now from the slides is a combination of frequencies of light. So white light just out in nature is actually a combination of all of the frequencies of light that are coming from the sun. But it turns out we only need a couple of frequencies in order to see white light. Specifically, these three. We need blue, green, and red. Combine blue, green, and red light and you get white light. And I know that sounds weird, but this is actually due to our biology. We only can actually perceive red, blue, and green due to the structure of our eyes. So we have red, blue, and green cones, which we'll talk about later when we get to talking about biology and structures of eyes and vision and so forth. But those structures can only really measure the amounts of red, green, and blue, and then put them together to make the other colors that we see. So if you put together those three colors, as you can see in this little diagram, where they overlap, they'll become white. So what we get is when we put these three colors together, we get what we call additive primary colors. And so if you add red and blue, normally you think, well, you add red and blue and you get purple. Well, that is working with things like pigments, but when you work with light, when you add red and blue light together, we perceive that as magenta. So it's not actually going to be purple with light, it's going to be magenta. If you add red and green together, again, if you're using paints, that's going to make a really ugly brown. But again, we're not working with pigments, we're working with light. And so when we add red and green together, we get yellow. Again, I know it sounds bizarre. If you have the ability to get some like filters or something to be able to try this, that would be, it's a lot of fun. Unfortunately, it's not something we were able to get together in time to put in your kits. So our last combination with light is blue and green. And when you mix blue and green together, you get cyan, a light blue color. And so these are our additive primary colors. If you add different combinations of all of these guys together, that's how you get the other colors. And so if you get a chance to look up close at some different screens, and that's what I have a shot of down here. These are different screens. So we've got a TV screen, a computer screen from a PC. This is an LCD screen. So is this one. What you're seeing are the individual, basically pixels from the screen way up close. This works on your laptop or on a cell phone if you can get a magnifier that can magnify enough. And you can see these individual dots. These individual dots are what create the colors on your screens. So they light up in different combinations to make the different colors on your screen. So if they're all lit up together, so for example, right here on the screen, all three of the dots are lit up next to each other to make that white light. Right here on the screen, all of the dots would be red, no blue or green. And then in this section, you're going to have the red and the blue lights lit up in order to show that magenta. In order to show things like orange or purple, it's going to be combinations of these lights at different strengths because it's the combinations of those wavelengths that make the different colors for us to perceive. So if, like I said, if you get a chance, it's kind of fun to be able to take a look at the different colors. Like if you get your screen to change to different colors and look at those pixels, it's really kind of cool. So speaking of these colors, there are opposites of primary colors, which is actually important when we get into doing things like printing. So green is magenta. So the opposites are literally the opposites on this setup. So remember we put together red and blue to get magenta. Well, magenta is opposite of green, which means if we add magenta light and green light together, they actually basically end up canceling each other out and make white light. I know it sounds really weird, but it basically is that you've got the red light frequencies and the blue light frequencies here in the magenta, and then you add them together with the green, and that gets you all three of them to get white. So the opposite of red is cyan, because it's the combination of the other two, and then the opposite of blue is yellow. So like I said, the addition of any color to its opposite is going to result in white light, because the opposite color is a combination of the other two colors that would make white light if they were combined anyway. Okay, so I told you in a previous video we're going to talk about selective reflection. So this is what makes objects look colored. So most objects don't emit light, but reflect light. So very few objects and organisms actually emit light. An example of one that could emit light would be something that has phosphorescence, like a lightning bug. But pretty much everything else is going to reflect light, and that's what's going to get us the color. So a material might absorb some of the light and then reflect the rest. So, for example, our little red ladybug down here, the red part of the ladybug appears red because that shell is absorbing all of the other wavelengths except for red. And so the white light comes in, all of the other wavelengths get absorbed, and then the red is what gets bounced to your eyes. So I don't know if you can see what color I have on today, but I have on purple. So all of the other wavelengths are going to be getting absorbed by my shirt, except for the ones down towards like indigo and violet, because those are the ones that are going to get reflected back to the camera in this case, so that your eyes can perceive it later. I've got, for example, my cell phone cover is blue, and so it's the same sort of idea. It appears blue because all of the other wavelengths of light are going to hit and be absorbed, but the blue is going to get bounced back, get reflected, and that's the color it's going to appear. So what happens if we change the wavelength of the light that's present? Because pretty much everything that we see on a daily basis is being shown under white light, has all the frequencies. But we can change the frequency, right? We can change the different wavelengths and frequencies of the light. And so that's what's going on. Oops, sorry, down here. I thought I had something else posted with this picture right here. So here's the original picture, and this is in white light. So we've got a playing card with the 3 of hearts, a bunch of grapes, and a green bell pepper. So the first thing that they did was, instead of white light, they used red light. So only the red wavelengths, red frequencies, were shown onto the same set of items. And so if you look, now that card looks blank. And most people are like, well, that doesn't make any sense. Why is the card blank now? But if you think about it, the card isn't blank. The card is white, which means it's going to reflect every color that hits it. That's what makes white objects look white. So any light that we shine on it is going to bounce back, is going to be reflected. So what we're seeing is the whole card is bouncing back the red light that we shine on it. It looks solid because it's the red card from the deck. So it's reflecting the red 3 of hearts, and it's reflecting the red light from the white portion of the card. So that's why this section looks like it's a solid card, because the red 3 of hearts is already red, and then the red from the white light we're using all is getting reflected back. And then you can see it makes sense, since the grapes have some purple in them, they'd have a little bit of red and a little bit of red on the bell peppers, but not much. We move over here. I bet you can guess what color they used here. They used the green wavelength. We can tell definitely it's green wavelength because the card turned green. That white part of the card is bouncing back the green wavelengths. And now you can see the 3 of hearts. It looks black, and that's because the only thing that it can reflect back is red, and it's absorbing everything else. So it's absorbing the green, and it's going to appear black. Now we can really see that green bell pepper because most of what it can reflect is green. And then if we move to the blue, you can tell blue because of the blue card, and you can tell that most of what those grapes have to reflect back is blue because they're the ones that are highlighted the most. So how does this tie to anything that you might run into, either in everyday life or in your arts? So if you never thought about it, why do objects look different inside versus outside? Well, it has to do with the lighting source. So these are the different frequency distributions for different light sources. So back here in the back, this is sunlight. So you can see that sunlight contains pretty much all of the frequencies in almost equal amounts. There's not as much of the indigo and violet, but everything else is pretty equal. Now let's take a look at what we would commonly see indoors. So we've got LEDs, very little of the red section, mostly orange, yellow, and green with a little bit of blue. Incandescents, mostly the reds and oranges and yellows, very little blue. And then the CFLs have some spikes. We've got some blue, good amount of blue, a spike of green, and some yellow, and a spike of orange. So actually the light that I have for my camera switches from different light sources. So let me switch mine so you can see how this might work. So I don't know if you'll be able to see, but that is the cooler light source. So this one, I believe, is more of an LED light source. That one is definitely more of an incandescent source. Even looking at it, I can tell it has more of these reds and oranges. And then this one's more probably in the CFL type range. It's got some more blues. It's got a little bit more of a mix to it. It may be in the LED range. It's hard to tell, but you can see that these different lights do have different effects on the appearance. All right, so selective transmission is related to selective reflection, but selective reflection only is with opaque objects. Selective transmission is with transparent objects. So I mentioned in a previous video that I'd come back to this. So the color of a transparent object depends on the color of light it transmits. So clear glass transmits all of the spectrum. So it will allow the entire visible spectrum in. On the other hand, the color of the glass, like I said, depends on what part it lets through. So in our stained glass here, the blue color that's down here is only letting through blue frequencies, okay? The more purple violet is going to block everything but the purple violet frequencies. The red is going to block everything but the red frequencies. I think you're probably catching on. And so combinations of these different materials can allow different frequencies of light to be able to come through, to be able to allow us to create these beautiful stained glass pieces. All right, the next video I'm going to talk about pigments and how that is going to be different from what we've been talking about with light.